There's one more thing in chapter 7 that I'd like to complete that was missed out, and that is work done by friction. So let's consider we have a horizontal surface and we apply a force that is also horizontal, and it pushes this object from its initial position to a final position. So this distance is a displacement from here to here, which we write as d, which is a vector, and that's the displacement, and that's the force. So the work done would be simply F dot d. But we also have friction, so the surface is rough, and the force of friction is given by F, which will be pointing to the left. So F is the force of friction, a force due to friction. Now, the work done by the force F, if we write it like this, is going to be F dot d, which is going to be F d cos theta these are the magnitudes times cos theta, and in this case F is this way and d is the same, so theta is 0 and it's just Fd. And the work done by friction is going to be the friction force dot the displacement, which is going to be F magnitude d magnitude and the cosine of the angle theta. But in this case the force of friction is this way and d is this way, and the angle is 180, and therefore it's going to be F d and minus 1 or minus F d, or separate magnitudes. So that's going to be the force of the work done by friction. Now, by using the work kinetic energy theorem, which says that the work done equals the change in the kinetic energy, the work in this case would be due to two forces. So there'll be two works, and we can write it as F dot d minus F, well, plus F dot d equals delta k, or for this particular case where they're all horizontal, it will just be Fd minus Fd. The reason why we put it here is there is always a confusion whether F and D are being in opposite directions. You would have a negative sign, and you already have a negative. So we just take the absolute value or the magnitude of the friction work and put a minus sign. So this will be the work done in this case.